Dr. Kufaitullah mentioned, under the supervision of Dr. Abdul Khalik. Today, I am going to talk on chaotic dynamics of a three-species food chain model. Actually, it is our recently published paper in Physica Scripta. Here is the outline of my talk: abstract, introduction, basic definition, dynamics behavior of the system. Actually, it is our proposed system. We use bifurcation theory and influence of initial condition, and then control chaos through OGY method. Then maximum Lyapunov exponent, and at the last conclusion of our talk. Here is the abstract. We analyze a discrete time food chain model to explore the impact of strong pressure on the entire chain. A bifurcation and stability theory is used to analyze equilibrium formation in system. In our proposed system, what we use stability theory and bifurcation theory, and then we give some numerical simulation, and what happened to our proposed system, we control that behavior, mean chaotic behavior of our proposed system. There are a lot of methods, but we use OGY method because our proposed system is a three-dimensional. Here is the link at the last. Food chain model actually first introduced by an ecologist, a UK ecologist, Charles Elton. He wrote a book on animal ecology. The concept of food chain was introduced. Later on, an ecologist, Raymond Lindman, contributed significantly to understanding ecosystem and food chain. Elton, here are the link. Here are the references of the book and the paper. And now the main question for new learner, for new researcher, what is a food chain model? Here is an example about what is basically food chain model. A series of organisms that depends on each other as source of food. Because our proposed system, in our proposed system, we analyze the pressure of strong prey. Here at the bottom, the leaf, and the top, here is the predator, and the rest of mid, the snake, the frog, the caterpillar or a prey, also the eagle itself a prey. But at this entire chain, it represents as predator. Human, lions, and eagles, and at the top of the food chain, plants are at the bottom. Here are some basic definition. What is bifurcation? Bifurcation actually it is a sudden qualitative change in the system. Either it is gone from stability to unstability, or unstability to stable condition. And because in our proposed system, we analyze our proposed system behave like produce Neimark-Sacker bifurcation. There are a lot of bifurcation exist. Period doubling bifurcation, transcritical bifurcation, Hope bifurcation, and so on. But here I provide only the definition of Neimark-Sacker bifurcation. Because our proposed system, we check that our proposed system produce Neimark-Sacker bifurcation. And Neimark-Sacker bifurcation, also known as secondary Hope bifurcation, occurs when a fixed point of a dynamical system. Here, please understand the difference between bifurcation and Neimark-Sacker bifurcation. Bifurcation is the only qualitative behavior of the whole system, but Neimark-Sacker bifurcation, it is basically occurs when a fixed point of dynamical system loses stability and a small amplitude. No, because Neimark-Sacker bifurcation depends on equilibrium, and what is meant by equilibrium point of a discrete dynamical system? An equilibrium point of a discrete dynamical system is a point where the system remains unchanged over iteration. It satisfies the condition. If the system satisfies this condition, then we find the equilibrium point. And also there are many other criteria to check the stability of the system. As I mentioned that our proposed system is a three-dimensional, so that's why we use this stability criteria. The equilibrium point is stable if all the eigenvalue, here lambda represent the eigenvalue of the system, lambda I less than 1 for I 1, 2, 3. This means that if all the eigenvalues are less than 1, then the equilibrium point will be stable. And if any eigenvalue satisfy the second condition, that is greater than 1, then the equilibrium point will be unstable. And if equilibrium point gives equal to 1, then we need to further analysis. And now next, motivation. Motivation, actually here we present two system. Actually these are continuous system. From this system we motivate and produce our discrete system. A food chain model based on Hosting and Powell has been examined the control strategy for chaotic population growth. Here is a link, Muhammad Ali Khan and et al. And the second one is this. No, we move our proposed system. Here is a proposed system, dynamical behavior of the system. An equivalent nonlinear difference equation model is considered for a three-species food chain based on the motivation of the system A and B. Here, in our system, here are the we use the parameter alpha, beta, gamma, rho, eta, and what these parameters actually represent in the system. Alpha, the intrinsic rate of growth of species X, beta, the size of the carrying capacity for species X, and gamma, the intrinsic growth rate of species Y depends on its environment, and rho and eta itself. First, as I mentioned in outline, first we find the equilibria of the system. All these work not doing manually, but we use Mathematica to find these equilibrium points. The system, our proposed system, has the following 5 possible equilibrium points. If you select another system, maybe your system give some extra equilibrium points, maybe 6, 7, 3, 2, or 4. It depends on the system. And the system many systems didn't give any equilibrium point. And classification of equilibrium points. What is the here I represent the equilibrium points of our proposed system E1, E2, E3, E4, E5. Are they stable or unstable? We find their stability after so many iterations. We use these value of the parameters alpha, beta, gamma, rho, and eta, and we saw E1 is a saddle point, means saddle. E2 itself saddle, E3 is also saddle. Depends on its eigenvalues, as I mentioned before, the criteria of stability. Next, now to check the behavior of a proposed system, we apply bifurcation theory. That is actually a norm theory. in order to understand the dynamical behavior of the system and to determine its equilibrium equation, one can be written in the following form. Here is the procedure how we can check the uh, chaotic behavior of the system by using the norm theory. First, we introduce three functions f, g, and h, and then the equilibrium point of equation 1 can be represented by the positive number. Equation 1 can be expanded into a Taylor series for linear stability analysis as follows. We use Taylor's series. Here you can see that fx, fy, here are as our proposed system is a discrete system. So then that's why fx represents the partial derivative of f with respect to x. Similarly, fy, fz, gx, gy, gz, hx, hy, az. Add these equilibrium points. Uh, to continue to check the behavior of our proposed system, we perform normal form equation 2 and 3 provide the following results at these equilibrium points. And the next, now let's suppose here are the matrix J represent M11, M12, M13. That's a Jacobian matrix. Actually the Jacobian matrix. And
Answer, answer, you have 3 to 4 minutes to wind up, please.
Okay, thank you, sir. The characteristic equation is now let's move to our numerical analysis. Here are the comparison as I told I mentioned that there are a lot of bifurcation exists. In our proposed system, we check that our proposed system produce only the Neimark-Sacker bifurcation. To verify that it is possible to exist another bifurcation in our proposed system, to we vary the values of parameters, and we check that there is no any other bifurcation exist in our proposed system. Here, here are some numerical examples. And then here are the then as every system depends on its initial condition, as we discuss about the chaotic behavior of the proposed system. To understand in every in all terms of chaotic behavior of the proposed system, we check it through norm theory to initial conditions. And in chaos, the initial condition have a great deal of influence. To examine the sensitivity of system to certain values to path or calculator under different initial condition. After to check the behavior of the proposed system through the changing of parameter values, we check the behavior of our proposed system through initial condition. We check that there are only two paths, but we didn't understand what is the actually difference between the dynamic behavior of the system when we change its initial condition. Then we further proceed, we change the values of initial condition, and we check that we can see that here on left side the green graph show that chaotic behavior, and the right and periodic behavior of the system, and so on. Now let's move the chaos control through OGY method. And after we understand the chaotic behavior, what our system actually produce the behavior, then we control the chaos that is produced in our proposed system through strategy by applying OGY method. Here are the structure of the OGY method. Please, the first order Taylor expansion can be used to describe equation 4 by referring to this. The main equation to apply to control the chaos in any system through OGY method. The main equation represented here by 5.
Answer, we have last minute.
Okay, thank you, sir. Okay. Now further, we actually what is the conclusion we represent in our paper? Investigating a discrete time food chain model under strong pressure, discuss types of equilibrium that may exist in the system, invariant curve undergo, and chaos is controlled using an improved OGY method. And number of iterations needed to maintain a stable periodic orbit. The control process does not damage the. We check that the OGY method, that is only the suitable method to control chaos in our proposed system. Any other system, if you apply another strategy, maybe damage the dynamics of the original system. But only the OGY method, the control process does not damage the dynamics of the original system. That is the main point of our paper. Thank you, sir. Hello, sir. Thank you.
Okay, Answer, thank you very much for your talk. And it was the first talk related to applied mathematics of bio mathematics. So if we have a question, please raise your hand.